Okay, good morning, everybody. So, the first talk today is by Arijeet on localization and edge modes in open quantum systems.
Right. To the organizers, if they're around, thank you for the invitation to present our work and organizing such a very interesting conference. I've learned a lot from all the talks, and it's a great collection of talks. So let me begin. So let me begin. To this audience, I don't think it needs any introduction why non-equilibrium states are interesting, and largely this interest has been driven by experiments, as has been highlighted in several talks before. But just to create the setting, I just want to highlight a couple of experiments which are sort of analog quantum simulators on analog quantum simulators, which observed non-equilibrium phenomena, which observed non-equilibrium phenomena such as many-body localization and quantum scars. So there's a sort of paradigmatic non-equilibrium states which we don't think there exist an equilibrium analog. They may be classical analogs, but they are certainly non-equilibrium states. So my motivation for this talk largely comes from these experiments where, although we assume that these phenomena exist in isolation, in any physical system, coupling to an environment is almost impossible to completely cut off. So your environment plays a very important role in the dynamics of these many-body quantum systems. And there are very fundamental questions about what role does environment play in quantum mechanics. Obviously the quantum measurement problem and the models of decoherence to understand what controls decoherence in many-body systems. It's only now that we are, even after 100 years of sort of playing with quantum mechanics, we are now beginning to understand the mechanisms of decoherence in some level of detail. Until now, they were limited to toy models like the Caldera-Leggett model and so on and so forth. But now we can sort of study them in actual physical systems and ask what role does the environment have. So this will be the setting of my talk. When we think of open quantum systems, as was highlighted in earlier talks, you can think of a Lindbladian evolution where you have an external environment, which is Markovian, which relaxes on very fast time scales, while the system dynamics are relatively slower than that. So if we make that assumption, so the dynamics can be written down in terms of a Lindblad operator. And within that dynamical framework, there are two ways of asking what kind of state the system is in. One is this quantum trajectory framework, where we start with a pure state, and as you evolve, you follow different trajectories based on the kind of jumps, which I'll define later in my talk, kind of jumps which take place on your state. And on the other hand, when you have an ensemble, that's an exponentially large number of states, which the system can sort of experience in some sense. So you can also take an average over all those states, and you can get a density matrix. So, there are these two ways of looking at a quantum state when it's coupled to an environment is quite rich, which doesn't exist in an isolated system. So that's why it's sort of, maybe there are various theoretical and conceptual motivations why we should be studying non-equilibrium states in open quantum systems. So one physical motivation could be, what is the fate of the quantum phenomena that we are interested in, like localization or scars, when you couple them to an environment? What are the kind of quantum phenomena which persist even in the presence of coupling to the environment? Maybe those are actually more robust and maybe more relevant for everyday for observations and sort of utilizing them for further technologies. And in some cases, obviously, environment plays a destructive role on quantum phenomena, like localization. But in certain cases, it may be possible that environment actually allows you to stabilize. If you have sufficient control on what the environment does on your system, you can actually stabilize some quantum phenomena. And I'll try to argue that that may be true for certain class of quantum states that we study in isolated systems. And then there is an even more interesting question, which has been highlighted in earlier talks, is can you have actually new phases of matter when you open the system to the environment, which there are no analogs in an isolated system? Are there new non-equilibrium phases, new phase transitions? Those are which are absence in an isolated system. So yeah, in Vedika's talk, she had talked about quantum circuits, and that's also an interesting sort of playground for these kinds of non-equilibrium states. So here you have unitary gates and quantum measurements, and you can ask the same question. The measurements sort of play the role of an environment. It renders the dynamics non-unitary, so to say. And then you can ask the same question, what happens to the quantum trajectories? And there are interesting phase transitions in the quantum trajectories of the many-body states, which people have studied, called measurement-induced phase transition, measurement-induced phases. But till now, in those settings, if you were to average over all the trajectories and then look at the density matrices, the density matrices are quite trivial, because in many of those cases, the density matrix is the identity. So it goes to infinite temperature. So that makes them experimentally hard to observe, these trajectory-driven phase transitions in the trajectories or phases of matter, which are only visible in the individual trajectories of the system. So that makes them sort of slightly experimentally less accessible. So now there's a great deal of work going on, new ideas for digital quantum simulation, how to sort of avoid that property where you have to look at individual trajectories. So that's a challenge, and people are coming up with new ideas, and that's an exciting sort of space to be in. But I will be focusing primarily on the Lindblad formalism. So it's sort of continuous time evolution of an open quantum system. And that has been highlighted before in Manas's talk and Takashi's talk earlier in the week. And you have some unitary time evolution given by some Hamiltonian or some Floquet operator. And you have some jump operators, which gives rise to dissipation in the system. So one aspect of this time evolution I would like to highlight is the role of symmetry, which is sort of somewhat richer than an isolated system. Because now you do not just have symmetries of the Hamiltonian or the unitary part, you also have a freedom to choose, not complete freedom. Experiments will sort of govern what kind of jump operators you have in a physical system, but that may depend on the symmetries of the bath and other properties of the bath. So that sort of already brings in sort of two kinds of symmetries which can affect dynamics in different ways. And I will try to show an example where these interplay between jump operators of the bath and the jump operators the operators in the Hamiltonian, they can give rise to interesting dynamical phenomena. So there are two classifications. So if your jump operators, if there is an operator which commutes with the jump operators and the Hamiltonian, all the jump operators, we call that a strong symmetry, then that operator is conserved identically. And then there's the notion of some kind of a unitary transformation, which which commutes with the Hamiltonian, but it doesn't really commute with the individual jump operators. And the case that we'll be interested in, where it sort of develops a phase and this phase will be plus or minus in the case that I will study later on in the talk. So that is sort of one sort of that will be the whole setting of the talk, looking at phases of matter which either have explicit symmetry that I impose or some kind of an emergent symmetry like in MBL, right? There are certain operators which can be conserved in an asymptotic sense. And what happens when you introduce some kind of dissipation or measurements on those emergent phases as well? What happens to the dynamics of those phases? So what are the features of those phases? So that's the setting of my talk. So I'll start with localization. Okay. So we'll look at, the first case I will show you is sort of the case of the MBL phenomena. And then, there's obviously debate about the stability of the phase, but I will be focusing on at large disorder where there is some kind of description which is maybe approximate. This MBL regime, we heard from David's talk, there's an MBL regime which has some local property which seems to be relatively long-lived. Now the question is, even if it eventually thermalizes, what is the role of measurements in actually maybe stabilizing localization in the first place? Because you could imagine that if you measure certain operators, if you measure operators which are sort of have overlaps with the tau z, your sort of approximate L bits, then maybe you can stabilize localization much more than in an isolated system. So let me sort of set the problem up. So the way we'll study this problem is perform some unitary time evolution for some time dt given by your the MBL Hamiltonian that I wrote down earlier. And then we'll make some probabilistic measurements on the state of this, on the state using some local operators. And the local operators can or may not have the symmetry. You can choose them what your local operators are, and they may or may not have the symmetry of your underlying Hamiltonian dynamics. So in one case, so if you want to if you want to do measurements in the, say, sigma z basis or sz basis, that has a large overlap with the approximate L bits. So what happens to the dynamics when you perform measurements of the local z operator? Here it's shown the usual time evolution of at p is equal to 0, and that has some sort of logarithmic growth. But then if you want to now introduce measurements on top of that logarithmic growth with some probability, at short time, it actually starts looking logarithmic. So at short time, it grows similar. But at sufficiently long enough time, actually what is plotted is I3, the tripartite mutual information. And at sufficiently long times, this sort of starts turning back, and the entanglement starts going to 0. So in the many-body localized phase, actually we checked quite carefully for the steady state for arbitrary weak measurement probability of this sigma z operator, the system flows to an area loss state. So the moment you introduce some kind of measurement in the sigma z basis, the state of the system completely flows to the area law phase. And this shows that this is there is some susceptibility of the MBL phase to operators which have overlaps with the, say, tau z operator, which reduces the phase to be in the area law phase for any finite probability. One can ask what happens if you now break the symmetry. So this is sort of the example of a weak symmetry, quote unquote. So if you measure in the X basis. So now, if the system didn't have any kind of underlying conservation law, X basis measurements should sort of behave in the same way. If it's still chaotic, or then the X basis measurement or the Z basis measurement shouldn't really differ from each other, but that is not the case. The moment you introduce any weak X basis measurements, your steady state now flows to a volume law. For arbitrary weak X basis measurements, so actually it's becomes scrambling. But when you go to very large measurement probability, you have a measurement-induced phase transition. So there's an instability of the MBL phase if you introduce an operator, measurement operator, which actually destroys the L bit, so quote unquote. So there is no, if there was no indication of L bit, this operator should have behaved in the same way as the sigma Z operator. But because of that, because this sort of scrambles the information in your L bit, starting from time t, even at short times, so you never really get to the point where you see any kind of MBL regime and you see, flow to the volume law phase for arbitrary weak measurement probability, and you have the area law phase at large enough measurement probability, which is just something in the X basis, which goes to an area law phase in the X basis. So what does the picture tell us? The picture tells us that the phase transitions are actually very different in the two bases. So if you have an X basis, so you have some measurement probability, this is phases as a function of measurement probability. So this operator, sort of, you can think of this operator as introducing a weak symmetry because you're measuring sort of not anything which has an overlap with the L-bit operators. So this is some kind of weak symmetry which breaks the symmetry in the unitary part of the system. So it breaks the symmetry in the unitary part of the system. So that's why the system immediately goes to the volume law phase. And at some point, there is actually a phase transition into the area law phase, which is like the measurement-induced phase transition. But if you were to actually measure the tau z, I mean, if you were exactly measuring the tau z operator, this system wouldn't evolve at all. It would be static, right? But if you measure in the z operators as z operator, then the system, as I showed, evolves for a bit, but then goes through a transient, and then you end up in the area law phase. So it's sort of area law phase throughout. There is no volume law phase in the case of sigma z measurements. So yeah, so that's the picture. The MBL phase actually behaves, or MBL regime, if you'd like to call that. The MBL regime behaves very differently for operators which have overlaps with the approximate L-bit operators, or if they're orthogonal to that. So it's the symmetry of, I call it symmetry because tau z's may be approximate. Yeah, this is trajectories. This is all trajectory. It's similar to the measurement-induced phase transit. So this one is, I mean, the critical exponents here actually look quite close to the measurement-induced of percolation. So we think once you introduce a tau x measurement, it actually delocalizes, even though it's a local measurement, it actually scrambles and delocalizes the system. So it goes to the volume law phase, and the critical exponents are very close to these percolation exponents, as far as we could tell. I mean, but it's for even finite size systems, it was, well, yeah. I mean, that's a good question, but as David said, I mean, numerics in finite size, you can never really see those rare samples. We have averaged over, I mean, so now there's a trajectory average and a disorder average. So we've averaged over both. So now, I mean, I'll actually take a step back. I will go back to studying the Anderson. So now MBL is interesting. I mean, but we solve the finite size effects and they're all the same problems. Now let's take a step back. What happens to the Anderson insulator in the first place? Maybe there's actually already interesting stuff even at the level of Anderson insulator. I mean, we have the sort of usual understanding that, oh, there's Mott's variable range hopping, there is diffusive transport once you introduce a coupling to the bath. But I mean, what happens with this new prism of looking at trajectories of those? Are there signatures of localization in the trajectories of the system? So yeah, so one can look at an Anderson insulator, which is in 1D with randoms on-site potential and hopping. And one can ask, now in this case, one can solve the problem for continuous time. So this is now in continuous time, not in a circuit kind of measurements, it's like weak measurements. So one can write down the stochastic Schrodinger equation to study the time evolution of some pure state. So you start with some pure state and then ask what happens to the wave function stochastically. So this is like a stochastic process, just like the projective measurements, just that it's sort of in continuous time. So it's sort of these are sort of, you integrate these equations and you can solve. You can actually solve them exactly because these for Gaussian states, the state remains Gaussian at all times, exactly in the sense of being free particles. So you have order L by L matrices. You're solving L by L matrices. So these are Gaussian states. So Gaussian states remain Gaussian states under this sort of prescription. And you can study pretty large system sizes. So the benefit is that you can study pretty large systems because it's non-interacting. It's not true for all kinds of dissipation that you will be able to do that, because certain forms of dissipation, the Gaussian initial state may not remain Gaussian under the action of this on-site dissipation, which is just some local noise. Jumper will be local density. This will measuring the number operator. No, just like this. So that, yeah, so that choice of the jump operator makes it solvable essentially. So yeah, so one can ask what happens to the entanglement of the pure state as we evolve as a function of measure. This is for some weak disorder as a function of measurement, this kappa or gamma in this case, which is the dissipation strength. So again, at large dissipation strength, the system goes to an area law, which is like what we expected. The system becomes disentangled, while at small dissipation, there is actually a log phase which opens up. So there is actually a log critical phase at small dissipation strength. And this one can understand. There is some analytic picture, not in the disordered case, but in the clean case, that it maps to some kind of a nonlinear sigma model. The trajectories, if you just write down the trajectories as some stat mech model, then it's a nonlinear sigma model, and this is got the BKT transition. So
this is non-interacting system, so you can evolve each particle independently. So where the entanglement comes from?
We start with a many-body state. Start with a many-body, so they have, the initial state is composed of many particles. So if you evolve a many-body state, even with a non-interacting model in a Gaussian model,
the initial state.
Initial state is a many-body state. Yeah. So as I said, at zero disorder, there is this works by Sebastian Diehl and Igor Gornia and Sasha Merlin. At zero disorder, there is putatively a phase transition between a log phase opens up, and then you at weak measurement strength, and there is an area law. There is still, I should point out that there's actually an ongoing discussion whether there is a log phase at zero disorder. So at zero disorder, I mean, the Karlsruhe group thinks that there is no log phase, and there could actually, the whole thing is an area law along the zero disorder line. But we are sort of focusing on disorder. So as you add disorder, we see that the system actually goes through a log law. The log phase actually, the disorder somewhat stabilizes the log law. You could say that the disorder actually helps forming the log phase. And as you go to very large measurement probability, you enter the area law phase. And this is a scaling, assuming a scaling form which is consistent with BKT. And one can, so here is a sort of the scaling collapse at weak disorder as a function of gamma, so along this cut. And that seems to, I mean, so we can go to relatively large system sizes because it's non-interacting. One can look at sort of hundreds of sites, while at weak dissipation as a function of disorder, one can also see some kind of a scaling collapse. Yeah. So yeah. So So that's the thing. I mean, at weak disorder, there is an instability of the localized phase to getting critical. So it's sort of the weak dissipation at weak disorder delocalizes. Yeah, at the bottom there, this is an area law phase starting from this along this line. There's an area. Well, the whole thing is area law, and then if you introduce weak, this opens up. I mean, so that's an interesting. So that's the picture we have at the moment. That any amount of dissipation actually opens up a critical phase. So that no, it's some kind of a Gaussian state, Gaussian free-form many-body. It's a many-body state, but it's a Gaussian state. We have averaged over initial states. We have averaged over initial states. Some class of Gaussian. I don't think it depends on the initial state. Yeah. So if you look at the Lindbladian evolution, then the average over there's nothing in. No, it doesn't depend on the initial state as well. Well, I mean, it says log in. I mean. Depends. I mean, it's not exact. It's not a fixed point state. Saturate. It saturates. I haven't shown the dynamics data. That's how we get this. I don't think so. I mean, we have averaged over initial states, so that doesn't have that. I mean, there may be fluctuations in it. If you take the average Lindblad, well, I'll come to that. So in the next slide I'll come to. Not in this model, but you can drive a phase transition in the Lindblad as well. Actually, but that's a different model. It doesn't have this. I don't know. I mean, that depends on what your jump operators are. Okay, let me quickly. Any other questions?
Dynamics data. What happens actually if you have the dynamics data of the? If you can calculate the von Neumann entropy.
Yeah.
As a function of time.
Yeah.
And what is the behavior you see? You see log t or?
No, there's no log t. I mean, it's just grows as.
How does it go as? Does it go as t or?
No, it doesn't go as. I mean, it saturates to a log law. It doesn't grow logarithmically. Let me get back to you. I mean, I don't want. Yeah, it doesn't grow as a log. That I'm sure. The question is in the critical phase. In the critical phase, it still could go linearly in time. It's possible. Yeah. Okay. So coming to the Dibyendu's question, I mean, can we get a localization transition in a Lindbladian itself? So you have to now look at a different kind of a model to get Lindbladian localization. So I won't be able to talk about them in detail, but I just want to flash. There are two sets of results. One is on long-range disordered Lindbladian model. This is quite similar to Manas's model for power law banded non-Hermitian model. But here we have looked at a Lindblad model where the jump operators now are no longer local. So you can have jump operators which have a spatial profile. So you can imagine there is some bath which couples to a large number of degrees of freedom, and the coupling strength decays as a power law away from the location of the bath. So the model is that you have a collection of baths which couple to your sort of system you're focused in, and the baths may not be homogeneous, all homogeneous at the same temperature. Yeah. So it is. So now, exactly, it is that transition, but now in the jump operators. So the localization transition happens in the jump operators, but these are non-Hermitian jump operators. So the steady state is not identity. It's only for Hermitian jump operators that the steady state is identity. For non-Hermitian jump operators, you could have steady states which are entangled. So here we see sort of our phase transition as a function of the power of this range. And at small p, you get a volume law phase in the entanglement negativity, while at large p, it goes into an area law phase. And you can again do a scaling collapse and find the phase transition, which is at p is equal, close to p is equal to 1, which is what the power law banded localization transition is. But now this transition is in the steady state, which is a mixed state of the system. So you can construct the steady state of this sort of Lindbladian, because again, this is a free Lindbladian. You can write it down in terms of free fermions. The Lindblad operators is just C dagger see. You're either putting in particles or taking out particles. And this phase transition occurs now in the mixed state, which is in the density matrix. And then there is also the non-Hermitian MBL problem, which is related in the Hatano-Nelson model, which you saw in Krishnendu's talk. And that is, as you introduce disorder, that has a very rich phase diagram. There are sort of two kinds of transition. One is, Krishnendu talked about the spectral transition. So there is a phase transition where the spectrum primarily becomes real. So in Krishnendu's talk, he showed that the entire spectrum becomes real. But here, even in this deep in the localized phase, the spectrum is actually primarily real, not really fully real. So there are imaginary eigenvalues, which makes the dynamics sort of not stationary in some sense. I mean, it'll decay to some sort of trivial steady state. But then there's the eigenstate stability instability transition, which is, I mean, we looked at various parts of the phase diagram as a function of interactions, G and disorder, the non-hermiticity, and there is a separation of these two instabilities in the system, at least at finite. So there are interesting questions. What is this sort of these real eigenvalues imply for the localization of the system? But I mean, I would just say that this is sort of also connects with probably resonances, and but we do find sort of two sort of crossover regimes which may be signifying, which may be relevant to the MBL transition, because this model maps to the standard MBL transition in the system. So if you go to G is equal to 0, it's the XXZ model, and that has some kind of crossover / transition, and these transitions connect. So this transition doesn't connect to the MBL crossover point, but the eigenstate one does. But this occurs at a larger disorder strength. So maybe this is sort of indicating of the true MBL transition sort of system. Maybe it's indicative of this pre-thermal regime. We don't know, because there are still lots of imaginary eigenvalues in that phase, even though there's the fraction goes to 0. So yeah, so with that, I mean, I'll skip the part on some. If you want to talk, I mean, is there any time? 2 minutes? I can. Yeah, 2 minutes. So the other idea is, now if you have in a clean system, you have symmetries. You can isolated system. You can have symmetry protected topological order, and then there are edge states associated with that. So now one can ask what happens if you introduce dissipation. So if you have a strong dissipation, you have strong symmetry in the dissipation. You choose a jump operator which commutes with this discrete Z2 cross Z2 symmetry in the Hamiltonian. You get a degenerate manifold of steady state, which is 16-fold degenerate. So these are the symmetries, strong symmetries. So you can think of, so these operators are conserved in the steady state. So you can think of them as some kind of logical qubits which survive even at infinite time in the density matrix. So you can sort of use that for storing quantum information, presumably. But once you break the symmetry, the weak symmetry, the system now decays, so you don't have memory in the density matrix, but you get sort of, if you introduce perturbations, in those case of strong symmetry, you can get very long lifetimes, some kind of a metastable lifetime of these edge modes in the system. And we can understand the spectrum in great detail, actually, of the Lindbladian. So not just the low-lying states, actually we can construct the full Lindbladian spectrum in the case of strong symmetry, where we don't, so this problem is sort of not fully integrable. There's some kind of fragmentation which takes place with which you can calculate the gap, not just the gap, but all the entire Lindbladian spectrum for this model. But even in the case when we have weak symmetry, where the topological order actually decays at some finite time, if you look at quantum trajectories, the quantum trajectories do carry information about the edge modes, and you can use that information to actually, if you monitor the boundary of the system, you can actually correct for the loss of information even even when the average density matrix decays to 0. So with that, I'd like to thank my collaborators on various projects, student Oliver, postdoc on the localization plus measurements, and then non-Hermitian MBL. It was done in collaboration with colleague at King's, Joe Basine, and the topological project was done with colleagues at a colleague at UCL and students, David, who did most of the work, Joseph and Albert. Thank you.
Thanks, Arijeet. Questions?
So, Arijeet, just one small comment about this, this non-Hermitian MBL thing. So, if you put in on-site disorder kind of stuff, you break translation symmetry, and that should automatically kill the reality of eigenspectrum, at least for some.
Yeah. It kills, but then it reintroduces at large disorder.
All?
Not all. That's
no, that's the thing. So all cannot happen. I mean, that one can show, actually.
That one can show that all.
Yeah, because, at least the way we proved this reality of eigenspectrum, the translational symmetry was a key element. If you did not have translational symmetry, this thing is not going to work. And you could show that at least some of them would get a complex.
But in the case of single particle, without interactions, that does happen. When you
only with open boundary condition. See, there it's usually with interacting system, the surprise was that there was a reality of eigenspectrum for a chain with periodic boundary condition.
Yeah.
With open boundary condition, it's known because you can do a similarity transformation and just make it real. But that's not what I'm talking about. Periodic boundary condition.
But this original non-interacting Hattano Lancer there, I mean, we looked at that.
Non-interacting disorder. Sure. But
disorder, that's what I'm trying to say. In the disordered non-interacting problem, the spectrum becomes fully real.
That's true. You can do a transformation, and
I mean, but that's related to it being localized, I think.
No, but the interacting one.
Yeah,
So my comment is only about that, not
clean
about
interacting.
Clean interacting.
Yeah, clean interacting.
The moment you put disorder in a clean and make it unclean, keeping the interaction might be so that not all things are going to be. Yeah. That's what I think. I don't know. I mean, maybe
we can discuss it.
Yeah.
So with these edge modes in the monitored SPTs, there's this notion of like average SPT, where like I guess it's a similar setting, except that you're looking at like the average density matrix. And in that case, if you have like strong symmetry in the sense that you described it, you can still get some kind of order, and I think including edge states. So is this different to that? Or is
in the case of strong symmetry, we do think the edge states at least some component of the edge state. So the edge state has a whole qubit. So if, depending on the kind of interactions you have, the edge state is either fully protected, its edge state is symmetry in the model, but then even if you introduce perturbations by preserving the symmetry, I didn't get a chance. So in the case where there are no perturbations and the edge states are exact symmetries, this model is as 16-fold degenerate, so the edge states will be preserved in the steady state. But even when you add perturbations which preserve the symmetry but preserve the strong symmetry, you get a 4-fold degenerate manifold, and there are other operators which sort of become metastable. So the two components, only the Z component of the edge mode remains a conserved quantity, while the X and Y component, they become metastable and they develop some kind of.
So is this for the average density matrix?
So this would be, this is the spectrum of the Lindblad.
Yeah. I see.
So this is the spectrum. So it is.
So you're no longer following trajectories?
No, this is all Lindbladian. So this trajectory was for the end, for the last part of the week.
Okay, I understand. Thanks.
More questions? Okay, so If not, let's thank Arijeet again.